Hi, in this tutorial we are going to solve some questions related to reactions and synthesis of ethers. The question asks us predict the products of the following reactions. Let's start from the first one. In the first part we have a phenol and we have a very strong base, sodium hydride. Okay, so what kind of reaction do we expect from this one? So basically it's going to be a deprotonation or acid-base reaction. Alcohol will act as an acid, sodium hydride, basically hydride ion, anion is going to act as a base, so that's going to be a deprotonation reaction. Let's write the product. The product we expect is a phenoxide anion. Plus we will have hydrogen gas. And if you look at here, phenoxide is actually a good nucleophile, and it's going to react in the second step of reaction with this halide, and this is a primary halide. So iodine or iodide is a good leaving group, so we will have an SN2 reaction here. Let's just show the mechanism. So oxygen in the phenoxide will act as a nucleophile, so it will attack the carbon bearing the leaving group halide, then the halide will leave. So what are we going to get? So we are going to end up with an ether. So we have 3 carbon here, 1, 2 and 3, plus we will have iodine or iodide anion as a leaving group. So basically this is one of the way of how we synthesize ethers, and its name, as you remember, Williamson ether synthesis. Let's look at the second question. In the second part of the question, we have a reaction. It's an ether, and we have a strong acid HBr. And as you remember, ethers are unreactive most of the time, but when we have strong acids and when we hit the reactions, they give rise to cleavage reactions. So let's look at what kind of ether is this. So this part of the ether, it's an alkyl group, so it's a primary. This carbon is primary and this carbon is secondary. So we expect that ether oxygen is going to be protonated. So Br will act as a nucleophile. So we will have an SN2 type of reactions here. But let's write first. So we have cyclohexyl propyl ether. So the first step is always a protonation. Then we will have the Br, bromide anion, and when we look at here, this is a primary carbon, this is a secondary carbon. So when we have primary and secondary, the nucleophile is going to attack the primary carbon because of the steric factors. So let's use the red color. It will attack here. Then this part will be a leaving group as an alcohol. Then the product is going to be cyclohexanol, plus we will have this substitution reaction. Okay, so basically when we heat or when we react ethers with strong acids, so the cleavage reaction is going to result in an alcohol and a halide here, and the substitution reaction will take place at primary carbon. Let's move to the next part. In the next part, again, we have an ether. This part of ether is T-butyl, and this part of ether is cyclohexyl. So it's a secondary and tertiary carbon on the ether functionality. And here we have 3-fluoroacetic acid. Basically, when you have T-butyl or a group, then can give us a stable carbocation, and also when we have a tertiary part here, basically we will have generally elimination product. and the elimination product will involve here the tertiary part, and we will have an alkene. Let's write the product. So we will have an alcohol here, and the elimination product will be this alkene. So generally, like if you have a T-butyl group here, if you have a 3-fluoroacetic acid, generally ethers will give rise to an elimination product here. Okay, let's move to next part of the question. In this part, we have an alcohol, and the beta carbon at alcohol has a electron withdrawing group, a halogen Br, and a good leaving group. So basically, when we use a strong base like sodium hydroxide, the hydrogen or the alcohol has enough acidity to lose its proton. So basically, there is going to be an acid-base reaction between alcohol and sodium hydroxide. There is going to be a deprotonation reaction. Let's write the product. So it's going to be an cyclobutoxide. Then we have here Br plus water. If you look at here, we in the same molecule we have a good nucleophile and a good leaving group. So basically, there is going to be an internal substitution reaction, an SN2 reaction. Let's use a red marker to show you the mechanism. So oxygen will act as a nucleophile, and bromine is going to act as a leaving group, and the product is going to be an epoxide, a cyclic ether, plus Br minus. So basically, when you have like beta halo alcohol, and if you react with sodium hydroxide, generally we end up with an epoxide. Let's move to next part of the question. Here again we have an epoxide, and it's going to react with an acid HCl, and in the next part we have again same epoxide, and it's going to react with sodium hydroxide. Let's start from the first part. As you remember, when we have epoxides, epoxide can give cleavage products in the presence of strong acids. Let's write the first part. The first part is always the protonation of alcohol with strong acid. Basically, ether oxygen will be protonated. Then we will have chloride anion. It's as a nucleophile. Here, like chloride anion is going to act as a nucleophile, so we will have a kind of like a substitution reaction. We have two sides, two electropositive carbon, this carbon and that carbon. So which one the nucleophilic attack site? Basically, when we have a primary and a tertiary carbon, generally like we will have a mixture of product, and the mixture of product will be like attack to tertiary carbon will involve an SN1 reaction, and attack of chloride nucleophile to the primary carbon will have an SN2 type of mechanism. So basically we can have this product. Let's write. So let's say I'm going to label this one as primary and this one is tertiary, and I will write the primary attack product first. So there is going to be like carbon carbon, and the chloride will be here. Then this part methyl methyl on this one, and we will have an OH group. Plus, if the attack occurs to tertiary carbon through SN1 mechanism, the product will be this. So again, this first and second carbon, and attack occur to tertiary carbon, and this bond will be broken, and we will have this product. So like general, like 60%, 40%, 50%, 40%, 50%, we can expect as a mixture of product. Okay, let's move to the last part of the question. We have again the same epoxide, but this time is the basic cleavage of epoxide. So when we have bases, or when we react bases with epoxide, attack is an SN2 attack to do less substituted or primary carbon. And so let's say that this oxygen, this hydroxide, is going to attack here, and this bond will open, and we will have this product. This part is the tertiary carbon, and it will have an OH group here, and this one has also another OH. So basically the difference between acid catalyzed and base catalyzed ether cleavage is that acid catalyzed ether cleavage, when you have primary and tertiary carbons, we will get a mixture of products. Tertiary carbon will give rise to SN1 type mechanism, and primary is going to give SN2 with the acid catalyzed cleavage reactions. But when we have a base, generally the attack occurs to less substituted carbon through an SN2 type of substitution reaction, and we will get 1,2-diols. Thank you so much for watching this video.